the way. Okay. So if I talk about the Cambridge O-level chemistry book, which we are currently using for O-level students, if we go according to what's given over here, so we would be covering number 1, states of matter, everything that was a part of first half of chapter 2, and then atoms, elements, and compound, everything that was there for the second half of chapter 2. But there is still some part of chapter 2 in the previous book I was hinting at missing, and that would be covered in this 14th chapter, experimental techniques and chemical analysis, apparatus used for measurement in chemistry and separating mixtures. So, which means we'd be covering chapter 14, 14.1 and 2, at least some of it, if not all of it. Then chapter 1, chapter 2. Also, there is a different periodic table chapter, which is chapter 9. So the whole of chapter 9. So chapter 1, chapter 2, chapter 9 completely. From chapter 14, only 14.1 and 14.2. Okay, if I talk about MOIS in specific, so MOIS, in your content page looks like this. So I'd be covering chapter 1, states of matter, chapter 2, the atomic structure completely. Again, since your new book looks like ours, so you'd find a periodic table somewhere here in chapter 13. So I'm going to finish up the entire chapter 13 for you. I'd also throw in some parts from chapter 14, which are properties of metal, maybe some uses of metal, and your chapter 22, chapter 21, experimental techniques and experimental design and separation techniques, some parts from 21.2, 21.3, and definitely the complete 21.3. Okay, so this is what we are going to cover from your book. We won't be doing these books. I just wanted to correlate them in the start so that you don't have a problem with it. Well, when you go through the course, you'll understand the topics. It would be easier for you to connect the dots yourself. If you've had any question previously, or if you have any question in upcoming days during we are doing this, you're most welcome to ask, and we can always clear up if any confusion arises, right? So I'm going to get back to our original book, and I'm going to start with chapter 2 of this book. Hopefully you've already downloaded the book from the link. This is going to act as a very good reference book. Whichever book you're currently using as per your school rules, this is going to be a very good second book for you. Okay, so chapters 2 starts on page number 21. So let's get to page number 21. In my previous class, I asked the students to learn how to annotate on my screen and get a little bit familiar with Zoom. So Moise, I'm going to ask you the same thing, be a little familiar with Zoom so that it's not a problem for you, how to annotate, answer my questions, stuff like that. A few YouTube videos of learning the basics of student side of Zoom is going to cut it for you, right? So moving on, let's start with the basics. So the very first thing we usually start with is the definition of matter. It's so basic that we are going to define it over here, but you are not going to see any kind of these definitions as a part of your paper. So it's just to build the basics, right? So matter is anything that has mass and that occupies space or that has volume, right? Anything like that, we call it matter. Now, matter can be distributed into 3 states you commonly call states of matter. And let me tell you, the states of matter are not limited to 3 at all. There are many, but we discuss the 3 since these are the most fundamental states. These are the ones that you're going to find around yourself most easily: solids, liquids, and gases. Now, changing temperature or changing pressure can change the state of the substance. So that means we can keep converting solids into liquids, liquids into gases, or vice versa. The key definition of matter is also given up over here, but let's get to the point where we discuss the differences between them. Now, in case of differences between solids, liquid, and gases, you're going to find many bases, and we discuss those bases and we explain those bases over here. So you're going to find the table in your books. You'll have the similar table in all of the books I've just discussed, in which they differentiate between solids, liquids, and gases. Sometimes they do in the form of tables, sometimes they do in the form of paragraph. So whatever that is, this is what each and every book is going to begin with. Now, we are going to take a few basics, like we are going to talk about volume, we're going to talk about density differences, shape differences, finally fluidity differences. But this is not limited to just these 4 points. Keep these 4 points in mind. We're going to start with this one, and we're going to move with more points. All right. So I'll be adding more points to the list. Let's start with these points over here. I would very much appreciate if you have your book or a rough piece of paper and a pencil in hand, because I'll ask you to keep writing more and more stuff either on the book directly or on a rough piece of paper, because that stuff is going to be acting like the missing portions of the book or the further explanatory parts which are going to help you with your revision. So if you have a pencil ready, that would be great. Now let's start with volume first. If I talk about volume, it's pretty easy, something you've studied in previous classes. We usually start discussing this in the science book, starting all the way from class 4, and we repeatedly do it in 4, 5, 6, 7. So I hope you remember from those classes that solids have fixed volume. Now that volume is usually not very well defined in chemistry, but that's really very well defined in mathematics. Now in mathematics, if you're going to discuss volume, they are going to give you it as a part of formula. So for anything, let's say you have a rubber close to you, a rubber that we commonly use to erase the pencil writings. Now that rubber must have some length. So we take that length and we multiply it by its width, and since it's a three-dimensional object, it must have a height. Now this formula is taught differently with different words. Sometimes it's length and width, sometimes it's length and breadth, sometimes it's length, width, and height. So no matter which word we use, it means the same thing. So we're talking about this direction, we're talking about this direction, and we're talking about the height, which we usually show like this. So that's how we calculate volume mathematically. And the same is carried out in physics as well as in chemistry. So everything solid must have a shape. Every shape must have some length, some width, or some height. So we can calculate that. For different shapes, we have different formulae for volume. This is usually the formula for volume for rectangular and square shapes. You have a different formula for circle, trapezium, and then you have cones, and then the list goes on. Mathematics is filled with formulae for different shapes for calculating their volumes. Well, that's not the topic of discussion. This was just for hint in correlating two subjects into one. All right. So let's get back to what we were discussing. So if solid has a fixed volume, so does the liquid. Although liquid is stored in a vessel, but it still has a fixed volume, that the volume of the vessel can always be measured, and we can find out the volume of liquid from there. In case of gas, there is no fixed volume, and the phrase that we commonly use to express it, which you're supposed to memorize and which you're supposed to reproduce whenever you're fighting with this logic in paper, so it expands to fill up the container. All right. We also use the phrase for this specific one, expands to fill all available space. Now, instead of filling up the container, which is a more childish term, talking about all available space gives you the idea that the gas might not be trapped in a small container every time. Instead, we may be talking about an entire room, an entire hall, an entire planet maybe. So the scope gets bigger and bigger, broader and broader, and the gas would expand to fill the area as much as it can. All right, that's why gases tend to travel. I hope you understand the point. I hope you understand that if there is no fixed volume on it, that's the way we can go with the expansion to a broader and broader category, no matter even if it has to expand to an entire planet. And that's what the air is currently doing. It has expanded to fill the entire available space on this planet. Outside of this planet boundaries, you won't find the same air, right? Any questions so far?
No, it's understood.
Good, good. It's simple, it's easier, so I hope you can understand it easily. So let's erase it, move on, talk about density. Okay, before I talk about density, I would love to go through the shape portion. So let's go with shape first and talk about density after, because this correlation is going to help you understand it better. So solid has a definite shape. And in order to explain volume, I already explained you with a lot of shapes: square, rectangle, circle, cone, semicircles. The list goes on. We have so many shapes in mathematics that can define solids. And there are many more which you are going to face in chemistry, new words. Okay. In case of liquids, there is no definite shape. It takes the shape of a container, something I've already explained while I was explaining volume. The same happens with gas. It also takes the shape of a container because it tries to expand. So there is no definite shape or there for liquid as well as for gas. Now, sometimes instead of using definite, students use the word fixed. Well, if you use the word fixed over here, definite over here, or fixed over here, or definite volume over here, both the words tend to mean the same thing and both can be considered correct, as per Cambridge. All right. So this gives you the idea about all of these in terms of their bifurcations or differences. Let's get back to density. Before I explain density, we need to formulate it. Now, density is not well formulated in chemistry, but you're going to find the formula in a much better explanatory terms in physics. So I'm going to use the same formula from physics, which is mass over volume. When we take a specific volume of an object, if the mass is too much, we call a high density. And for same specific volume, for a fair comparison, if the mass is less, we call it a low density. Which means the things that tend to be heavy for the same size have high density, and the things that are light for the same volume are supposed to have low density. That's how we define it. Now, of course, density would have the same units the mass or volume does most commonly, so we can use those units. Those units can be different at different points. Well, whichever units you use, it's going to define density in the same way, and the units may change. We do not discuss these units so much in chemistry, but this definitely is going to be a part of the basics of physics. Now, as soon as we put it this way, we come up with three separate answers for solid, liquids, and gases. Now, when you see that's high for solid, that's moderate for liquids, and that's actually low for gases. But there is a simple point that might be a little bit confusing. In liquids, we write moderate to high. Now, when I start explaining this, I usually tend to ask my students to keep some examples in mind to have a better idea of what we are talking about. So if I put ice as an example of solid and the same one, water, as an example of its liquid state, and the counterpart, of course, you can write steam, you can write vapors, whichever one you prefer, as a part of gas for the same one. So definitely ice seems to be heavier, it's solid, more of the water is packed into the place, into the specific volume, right? For liquid, it's moderate to high, for vapors it's different. Now, if I go with different examples, it can give you a better understanding. Let's talk about different examples. Now, if I talk about examples for moderate to high, and I put water as an example of moderate, and I put honey as an example of high, I hope you would easily be able to understand the difference. Now, both of them are liquid, but one of them is heavier than the other. One of them definitely has a different density than the other. Now, this doesn't just belong to density. If I jump to the next part, fluidity, and I connect it with this one, you'd understand what I'm about to say. So I'm quickly going to connect fluidity to it. I'm going to jump back to density and explain fluidity and density side by side. It's going to give you a very good comparison. Now, fluidity means they can flow. Now, you can see a simple line written at the bottom that the gases and liquids are together known as fluids. Fluid means something that can flow, right? So, any state of matter that can flow can be considered as a fluid. Since liquids and gases can flow, they are considered as fluids. Solids are not considered as fluids because they can't flow. So it's pretty simple. Solid does not flow. Liquid generally flows easily, and gases definitely flow easily. Instead of using easily, even if you use easiest, that would be the most better thing to say. Right? Now connect this fluidity with moderate to high density. You have a glass of water, you tilt it upside down, instantly the water would come out. You have the same for a jar of honey. You have to wait. Mr. Honey, you need to come out. We're waiting, we're waiting, we're waiting. You can literally count the seconds of your wait time for honey to come out of the jar. Now, this clearly explains the density difference, moderate and high, and along with that, the fluidity that density affects. I hope if you connect both of the dots, you understand what I'm talking about. Any questions so far?
No.
Okay, so what I tend to do is to not stop at this point. I actually take it a few notches more so that you can understand it better. What I'm going to do is that I'm going to stop sharing over here. We're going to get to a whiteboard and we are going to discuss it over there. I hope you can see my screen. Okay,
Yes,
so
we can.
let's talk about solids, liquids, and gases. And let's talk about different properties. Now we are already done with density, shape, volume, and fluidity. So let's talk about more. Let's first start with, come on. This tends to happen every time. Please bear with me. Okay, so let's start with examples. Let's say we talk about ice, water, and either vapors or steam, whichever one you'd like to put. Now, I tend to actually explain it with the help of a diagram. The properties I'm going to explain further are better described in a diagram. So I have this much packing of ice. The particles would be close to one another, so much so that they would be arranged in proper layers and touching one another. In case of water, they would be close, but there would be some irregularity in the particles, and of course lesser number of particles. And in case of gas, the particles are going to be far away from one another. I shouldn't be actually drawing this. If I do that, they won't be irregular. So let's draw some particles irregularly, like this. Okay, so what I tend to explain is the arrangement. Now these diagrams are going to help you a lot with this. The arrangement with the words we tend to use are regular or irregular. Now the ice is packed into proper lines which can be divided into rows horizontally and columns vertically. So much so you would be able to see 3 rows going ahead like this, the first row, this, the second row, this, the third row. So much so every column, first, second, third, fourth, you can define them. So if I write the word regular for this arrangement, it would be very precise. It would be completely explaining the stuff I want to explain. And I'll have to definitely use the words irregular for both liquids and gases because they definitely aren't arranged in a regular pattern. Now, it's not just the arrangement that we are concerned about, it's also the packing. Now, in case of solids, the structure is tightly packed, so much so every particle is touching another particle and they don't have much area to move around. And less tightly would be the right term to use for liquids, and far away from one another would be much better explanation for gas. Although my diagram is so small that the particle seems to be closer, but if you compare it with water and ice, they're definitely not that close. I hope you get the point. Okay, moving on. Now, next term is commonly known as intermolecular spaces. We commonly write it as IMS. Well, if you use the whole term, that's better. Intermolecular spaces is actually space between the particles. So that's least for solids, and that's most for gases, and that's mediocre for liquids. You can call it medium, you can call it something in between, so solids and gases, or mediocre simply. Right? If I tend to add more points to it, just a second. Any questions so far?
No.
Now, next would be type of motion. Now, before I go any further, I need to give you a key. What are the different types of motions that we usually see in particles? Now, first one would be motion in a straight line. We usually tend to call it linear motion. We also may call it translational motion. Translational motion also means motion in a straight line. Now, next up would be circular motion. Pretty obvious. A little to the left, a little to the right, commonly known as vibrational motion. It is also known as to and fro motion, or a particle may actually revolve or rotate around its axis, so axial or rotational motion. Okay, rotational is the motion that Earth is doing around its own axis that we usually teach in geography to tell you that how the 24-hour cycle or the day and night cycle is occurring. Earth is rotating around its own axis, and that's how we get day and night. Circular motion is the motion which Earth is doing around the sun and which approximately takes 365, 1/4 days in a year to complete, which actually brings for us the 4 different seasons. So I hope the revolution or the rotational motion is something that you can understand. Now, these type of motions, if all mixed together, right, or if I say something like this, right, this would be random motion. So if I talk about solids, since they don't have enough space to move around, the only thing they can do is vibrational motion. A little bit to the left, they strike another molecule on their left. A little bit to the right, they strike the molecule on their right, and they can't move any further. They're so closely packed, they don't even have the space to. Moving on, for liquids, the phrase that we commonly use, slide past one another. They tend to move very small distances, and in doing so, they sometimes jump over or slide over one another, which definitely gives water the capacity to flow. Since the particles keep sliding past one another, they keep flowing. I hope it gives you a very good imaginative idea of how water can flow. Lastly, for gases, it's random motion. Now, let me clarify. Gases mostly go in linear or translational motions, which means they go in straight direction. But since they tend to strike or collide with the particles of the same gas, maybe the particles of different gas, maybe the wall of the container, maybe the lid of the container, so they tend to moving in straight lines, colliding, changing directions, colliding again, and in this whole process, their motion becomes random. For example, the air particles. The air particle keep moving towards us, then they may strike our face, they may change their direction, and this happens with the air coming from the fan, which we actually enjoy in summers. Now, in summers, you definitely feel hot. When the air from the fan strikes your face, you have a pretty good feeling. But think about the molecules that are striking your face. Yeah, they're definitely were traveling in a straight line. Now, after collision, they're going to change the direction and move in the opposite side, maybe in a totally different direction. So, random motion. Random means a mixture of many kinds of motion. Okay? So, I hope this gives you a complete idea about the differences of solids, liquids, and gases. Are we good?
Yes.
Any questions so far?
No.
Okay, since this is giving us a problem and we are done with this anyway, you'll get the picture afterwards. I'm going to stop sharing and I'm going to get back to the book. Now, as soon I hope you can see the book. As soon as we're done with the differences between solids, liquids, and gases, the very next topic would be changes in physical state. So we'll start talking about how we can convert liquids, solids, or gases into one another. And this one big diagram is going to help us with every single process there is. That's what we are supposed to start in the next sitting. I guess that's all for today.